2.4. Number 9. All right, so this is where we are given cardinalities of various sets in set notation. I'm going to jot them all down real quick. Got the cardinality of A has 20 elements. Cardinality of the intersection of 3 sets A, B, and C is given to be 7. Cardinality of A intersects C is 16. Cardinality of A intersect B complement is 11. Cardinality of B intersect C is 12. Cardinality of A complement intersect B complement intersect C complement is 22. Cardinality of B intersect C complement is 5. And cardinality of B union C is 40. All right. Sketch a real quick. All right, so we got 3 sets. Interlocking circles. A, B, and C. Sets A, B, and C. All right. So what we want to do is figure out what each region, and we have 8 regions, the number of elements that would be in each region. And we always want to start here, where all 3 overlap, or the intersection of all 3, which is given to be 7 elements that are in A and B and C. So that's 7. And I have used that piece of information. And then we'll move our way out to where 2 of the 3 overlap. So I can look right here, and I've got A intersects C. That is A and C. That now A and C is all of this, which means we've already counted 7 of the total of which was 16. So we would need 9 more to get that total of 16, or 16 minus 7 is 9, however you want to calculate it. But now we've got A intersects C, a total of 16. So now I've used that. All right, now here I've got B intersects C, which would be here, and it's given to be 12. So I would need 5 more to get my total of 12. So I've used that. So let's see what else we have to use. Now, if I look at this one right here, now it's A intersect B complement. So remember, that would be the overlap of A. So it'd have to be an A, and everything outside of B. So B complement. Now, everything outside of B overlapping with A would be this region and this region. So it's 2 regions, of which I know 1. All right, so it says that that total is 11. That is between this region and this region. I'd have to add up to be 11, which means I need 2 more. Are we good with that? All right, so we can do the same thing here. I've got B intersects C complement. Now, unfortunately, right now, when I look to use it, here are the 2 regions. B now outside of C, overlapping with B would be these two regions, and I don't know either one of them, so I can't use it yet. This one's, I could have done any time. If A complement intersect B complement intersect C complement is outside of all three, which means we've got 22 here. So, all right, so let's see what else we could come up with. We'll go back and grab this one. It says the cardinality of A has to be 20. So everything in A, that's 4 regions that comprise A, have to add up to be 20, of which I know 3 of the 4. So 2 plus 9 is 11, and 11 plus 7 is 18, which so that says I need 2 more. So I have a total of 18 in A. Now I can go back to this one. B intersects C complement. So outside of C, overlapping with B would be these 2 regions. And it says it's 5, so I would need 3 more to get my total of 5. That leaves this, B union C. Now that's all the regions making up B or C. So there's 6 of them, here, 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 and here. So I need to add up the 5 I know. That would be 5 plus 5 is 10, plus 7 is 17, plus 9 is 26. So 40 minus 26 should be 14. And that would do it. Now, I'll go ahead and quickly punch in the numbers. Just to verify. 7, 9, and 5, 14, and 22. And that is it. So that's all we had to do. Any questions on that one? Another problem from 2.4. All right, if you think of something before we end today, you can still ask and we'll work it. My plan for today is I want to talk about some infinite set concepts that we haven't talked about previously. And then I'm going to assign a quiz, which basically will cover through all the sections we covered in set theory. That is, it's basically a review for the exam, which I'm going to assign on Wednesday. And so, without further ado, some infinite sets. So what we basically want to do here in talking about infinite sets is come up with a definition, a precise definition of what an infinite set is. And this is going to be so something much more substantial than it just goes on forever and ever and ever without end. All right, so in order to get there, to build that definition, I need to talk about a one-to-one correspondence. So and one-to-one correspondence this between sets A and B if and only if all the elements of A correspond, hold on. Correspond to one and only one element of B. And so I don't have to write this all again by saying all the elements of B correspond to one and only one element of A. I'm just going to say and vice versa. All right. So this is what we mean by one-to-one correspondence. We can abbreviate this with a 1-1. All right. So looking at what this means, let's say I have a set A and it has the elements 1, 2, 3. And a set B and it's got the elements A, B, C. Now, I can do this. Use little arrows. Now, this would mean 1 corresponds to A, and 2 corresponds to B, and 3 corresponds to C, and A corresponds to 1, B to 2, C to 3. And so it would meet our definition. Every element here only corresponds to one element here and vice versa. We also note that that's not the only one-to-one correspondence I can establish. So I'm going to show another. There's more than 2, but I'm just going to show one more. So if I had 1, 2, 3, A, B, C, I could do this. 1 goes to B, 2 to A, 3 to C. And there would be others. In fact, there would be 6 total. So write up a little thing here. If there is a one-to-one correspondence between 2 sets, there is so if you know you got 1 and you're wondering, well, how many would I have total? How many different one-to-one correspondences could I show between 2 sets? It is in exclamation point. That's not actually an exclamation point. We'll talk about that in a second. And as always, n is the number of things in the set. Boy. So, cardinality sets. Okay, so one thing to observe, it would appear, we are assuming, if n is the cardinality of the sets, the only way there can be a one-to-one correspondence between 2 sets is if they have the same cardinality, and that is true. So essentially, it says they're the same size. They have the same cardinality. If they two sets have different cardinalities, then there's not going to be a one-to-one correspondence between them. Secondly, what is this? So for those, anybody know what this means?
Does it mean factorial or something?
That's exactly it. It was called factorial. So, and simply put, it does this. Let's just say you, as an example, had 4 factorial. Then this is 4 times 3 times 2 times 1. You start at that number, that counting number, and multiply down through the counting numbers to 1. And then whatever that product is. So in this case, you'd be 24. 3 factorial would be 6. So the example I just did here, there would actually be 6 different one-to-one correspondences you could show. 2 sets that had cardinalities of 4 would actually have 24 different one-to-one correspondences between them. If you had 2 sets with 5, it would be 120 different one-to-one correspondences between them, so on and so forth. Okay. Turn the page. Now, just to exemplify that, if we had a set A and it had the elements 1, 2, 3, 4, and a set B, and it had a cardinality of 3, so it just has A, B, and C, then you cannot establish a one-to-one correspondence between them. Now, I could do that, but as soon as I then tried to take 4, it wouldn't matter which one I corresponded it to. Let's say I just did that. I'm not going to meet the definition. Give me a second. I got to try to shut my dogs up. Sorry about that, guys. I don't know if you could hear them barking, but it was really loud where I was here. Apparently there was a cat outside the window. All right, so anyway, we're not going to be able to meet the definition of one-to-one correspondence because going back from B to A, I would have C corresponding to 2 different values or 2 different elements of A. So only sets which have exactly the same cardinality can have a one-to-one correspondence between them. And we know how we could count up how many one-to-one correspondences we would have. So if 2 sets have a one-to-one correspondence between them, they have the same cardinality. That is the same number. Man. Same cardinality, same number of elements. And are said to be equivalent. So we are differentiating now between, with sets, the idea of being equal and equivalent. So essentially equivalent just means they have the same number of elements. They may be completely disjoint. They may not have a single element common between them, where equal sets are subsets of one another. So equal sets would be equivalent because equal sets would have to have the same cardinality, but equivalent sets are not equal. So the door doesn't swing both ways. Traditionally, you have two sets. You had a set M, and it had a cardinality of 3, and a set N, and it had a cardinality of 3. Then M and N are equivalent sets. And notationally, we use a tilde. And we'd say M, and this would mean M is equivalent to N. And as soon as you see that tilde mark, you know there's at least one, we know there would be a total of 6, but there is a 1-to-1 correspondence between them. All right, so at this point, you got to be asking yourself, so you said you're going to talk about infinite sets and actually define them. We haven't seen anything about infinite sets yet. So let's take sets of numbers, which we started with when we started talking about sets. Let's take the counting numbers, the naturals. We'll put them in listing form. All right. And let's take the set of whole numbers. Now remember, the whole numbers were the naturals, and I threw in the number 0. Okay. Now, you might, and I love asking this question, which set's bigger? And
W.
What's that?
W.
Okay. And that's a fair answer at this point. You'll get 1 or 2 answers to that question initially. One, you're going to say the whole numbers are bigger because they've got an extra element that the naturals don't have. And so that's a legitimate answer. You might also say, well, they're both infinite, and trying to wrap her, so it goes on forever and ever and ever. So they're the same size. Well, here they are the same size, actually. But we're going to find out here later. Well, this gets kind of mind-blowing towards the end of this discussion. But let's just show that they are the same size. Now, if they're the same size, there's a 1-to-1 correspondence between them. So that's why we established this idea of 1-to-1 correspondence. So I'm putting these arrows in, matching up elements. Now, that in and of itself doesn't show that they're the same size. What you have to be able to do is, and generally, if we would really get into detail with this, we would actually write some math formulas comparing the two. But as long as we can verbalize it and be 100% sure, if there's a 1-to-1 correspondence between them, then any natural number you give me, I can give you the one whole number to which it corresponds. And any whole number you give me, I can always give you the natural number to which it corresponds. And if I can establish that, then there's a 1-to-1 correspondence between them. And ergo, they are the same size. Well, I can do that. Basically, it works this way between the naturals and the wholes. Any natural number you give me is going to correspond to a whole number 1 less than it. So you give me any natural number you want, I can always tell you the one whole number to which it corresponds. And any whole number you give me corresponds to a natural that is 1 more than it. And we could actually, this one, write a formula for, formulate it. So let's say I've got n, then here it's going to correspond to n minus 1. And thus and therefore, these two sets are by definition the same size. So we can say the naturals are equivalent to the whole numbers. Now that in itself doesn't get too mind-blowing, other than you know, because you can say, oh, they're infinite sets, so it makes sense. Infinity is the same size as infinity, and but we're going to find out that's not true. But it does completely match up with the definition. I'm going to do one more. The naturals and the integers. Now remember the integers. We used a z look like this. And it was ... -3, -2, -1, 0, 1, 2, 3, ... That was the integers. It was the whole numbers plus all the negative natural numbers. I'm going to show that the naturals and the integers are the same size. That is, show a 1-to-1 correspondence between them. Now, the way I'll go about showing this, first I'll write out the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8. That's enough. 9. ... So when I do the integers, though, this time to show this 1-to-1 correspondence, I'm going to go back and remember it doesn't matter the order which I write elements. I can write them in any order I want as long as all the elements are there. So I'm going to reorder the integers. Typically, we always write them this way, but we could do it this way. I'm going to put a 0. I'm going to put 1, then -1, then 2, -2, 3, -3. So I've definitely established a pattern. And that would give me, by that pattern, all the integers. And I'm going to put the little arrows in. Okay. Now remember, as long as you give me whatever natural number you want, I can tell you exactly the one integer to which it corresponds. And vice versa, we have a 1-to-1 correspondence between these two sets. So what I'm first going to do is I'm going to say, making an observation, and we're just going to verbalize it. All the even counting numbers, 2, 4, 6, 8, correspond to an integer that is half of it. That is divided by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. 6 divided by 2 is 3. 8 divided by 4 is 4, etc., etc. And then all the what? Positive integers, that is 1, 2, 3, 4, correspond to an integer that is twice it, that is times 2. All right, so that takes care of those. Now, as far as the odd natural numbers, we'll put 1 with 0, just say that. Now, this one gets a little bit wordy, but we can word it out so that it will always work. So it would appear all I really need to do here is I got 3 going to what? -1. So, and I got 5 going to what? -2. So if you, again, this is not the most mathematical way, but it will work. If you reduce, so you take the odd integers, reduce it by 1, and then divide by 2, and then make it negative. That is, okay, take away 1, gives you 2, divide by 2 gives you 1, make it negative. Take the 5, take away 1 gives me 4, divide by 2 is 2, make it negative. Take the 7, take away 1 gives you 6, divide by 2 is 3, and make it negative. Take 9, take away 1 is 8, divide by 2 is 4, and make it negative. And that will work every single time. So I have a way that I can show one-to-one correspondence between the naturals and the integers. They are the same size. Now, believe it or not, I can do it with and I'm not going to do it. I can do it between the naturals and the rationals, all the possible fractions and any number that can be written as a fraction. It gets kind of complicated, but it can be done. And so at the end of the day, that means that the naturals are the same size as the whole numbers, which are the same size as the integers, which are the same size as the rationals. Now, we have used this word cardinality for sets, and we say it's a number of elements in the set. What would be the cardinality of these sets? Because they're all the same size. So since I can't just attach some counting number to that, because we know these are infinite sets. So remember, again, we're building to a definition of infinite set. We're almost there. That cardinality of, say, the naturals, and then any set which is the same size as it. I have a hard time drawing this symbol. We'll just leave it like that. So that is my poor rendition of the capital letter Aleph, which is the first letter of the Hebrew alphabet. And then that's a P. And the subscript 0 is where the null comes from, Aleph null. So this symbol was created, and it is the cardinality of all 4 of those sets of numbers. They all are the same size. Now, this is where it really gets mind-blowing. I'm not going to, again, because we're not testing on it. And you would never really go this far. Now, what you will do is show the sets of numbers in an elementary setting. You will define naturals, you will define whole numbers, you will define the integers, you will define the rationals, that is all the fractions, by 4th grade, and eventually talk about real numbers, so definitely by the 5th grade, you have talked about irrational numbers, and because you've talked about numbers in decimal form, and you've talked about numbers in decimal form that never repeat, never terminate, such as pi or e or square root of 2, etc. And so you've got a little bit deeper understanding of these sets of numbers now and how they relate to one another. Well, the mind-blowing thing is I can show this, definitively, there is not a one-to-one correspondence between the naturals and the irrationals. Ergo, they are not the same size. And by extension, there's not a one-to-one correspondence between the naturals and the reals, which, since they're both infinite sets, and you can conclusively show there's not a one-to-one correspondence between them, they're not the same size. So the logical implication of that is there are different sizes of infinity, which, that'll just melt your brain. I can't visualize what one size of infinity looks like, let alone multiple sizes. But it is true. Now, just the cardinality of the reals has this little script C. So, and you can see some heavy mathematics show that that's actually bigger than Aleph null. All right. So one last thing I want to do with this discussion is define what is it that makes an infinite set. and give a rigorous definition. So I want to go back to, we were at the beginning of set, we're talking about sets, and we defined subset. Set A is a subset of a set B if and only if all the elements of A are in B. And then we defined proper subset. Now, A is a proper subset of B if all the elements of A are in B, and B has something A doesn't have. So I'm just going to look at these two. And we've established there's a one-to-one correspondence between the naturals and the wholes. It also turns out that the naturals are a proper subset of the wholes, because all the natural numbers are in the wholes, and the wholes have something that the naturals don't have, namely 0. Now, but yet there's a one-to-one correspondence between them. If I have the set, right here, 1, 2, 3, and the set 2, 3, there is this set right here, so we'll call it B. We'll call this A. B is a proper subset of A, but there's definitely not a one-to-one correspondence between them. This has a cardinality of 3, this has a cardinality of 2. So basically, the only way you can have a one-to-one correspondence between two sets where one is a proper subset of the other is if that set was infinite. And that is the basis of our definition. So a set is an infinite set if and only if it can be placed into a one-to-one correspondence with a proper subset of itself. Otherwise, it is a finite set. And there is our definition of infinite set. So very precise. All right.